Well, anyhow, Elena is fine. So, who have heard about that formula? Please raise your hands.
Not me.
Not many, as expected. So, it'll be of great interest for you. So, let's start. Let's speak about plots. What can we do with a function or formula or any other equation, or any equation if you like? We can plot it, we can solve it, we can examine it, and, well, let's focus on plots. Here's rather than a torus plot, series of x, and just waving through the infinity. And this function is a bit more complicated. It's in polar coordinates, and still, when plotted, it will result in romantic and beautiful heart-shaped advantage. The next one looks like intense wizardry, but still, again, when plotted, it will result in somewhat notorious simple Batman equation. Anyhow, how complex and hard anything we still can say much about it. We can say when it rises, when it falls, term maximum, minimum, and so on and so forth. But what can we tell about a function or formula that plots itself? So, to understand recursion, you have to understand recursion. That statement is well known and it's, well, just easy to remember. And recursion is a part of self-referential things. And when we speak of self-reference, the drawing of Moritz Escher will describe it with enough elements. Hand drawing, the other hand, that in its order draws the news one. Easy as a quiet thing. So, you all know basic operations like power operator, multiplication, division, so on and so forth. But we'll have to know a little bit more. Floor function. It's just basically rounding to the smallest integer value possible. For example, floor of 2 will be 1.2, floor of pi will be pi, and floor of 3.9999 to infinity will result in also 3. And modular operator is just a reminder of the division. So if you take mod of 23.5, you will result in 3. You can just check it for something reason. So, Jeff Tucker. He is a computer scientist at the University of Toronto. And one day he was working on a project of bitmapping images. So bitmap images, and he came across a formula that looked very strange and that decoded some strange, very unusual plot. And by the way, sorry for the picture, that's the only picture I found on the web, and that's not really much information. I would have found much more information than probably the university is. So, let some k integer k value be 4, 8, 5, I can do this really well, 8, 4, 5, 0, 6, and the rest-ish. Quite a long number, but I have to ask you to remember it. We'll need it later. And the formula is this. You can't see any recursion here, neither self-reference, so you may wonder why it's called like this, but we'll get to that later also. And you can't see any k value here, by the way. Well, you'll also get to that later. So, instead of doing self-reference, what it does is when you put all the possible values of x and y, you will result in a big binary number, just zeros and ones, located in a grid of infinity by 106 columns. Not much, but still. So if you take just a small piece of it, of 17 by 106, you'll result in big map. Something just zeros and ones and nothing more. But from behind of the disorder, you may see something rather familiar. And if you don't, then I'd like to highlight once. Magic. So let's take a closer look. If you take one column, you'll receive a binary number. And what shall we do is turn all the ones to black squares and all the zeros to white squares. And we'll result in something like this. And if we do this repeatedly for each column and each row, will result in an image. So what this formula does actually says us which ones have to be black and which zeros have to be white. And if we go upwards the y-axis long way up, we will suddenly receive this image. And the k value is 4, 8, 5, and ish. Well, quite familiar one. So, this is exactly the bitmap image that depicts the formula itself. And actually, we can receive this image if we go k points upwards the y-axis. So, It looks like magic, but no magic involved. If we just add 17, we'll receive this image, but with one dot in the left corner, left lower corner, you can see. And if we put just 17, will result in that dot, and only that dot. And if we multiply it by 1/16, we'll have something like this. So what this formula actually does, it just fills the grid with all possible configurations of black and white squares. And so this is a formula of everything because you can fit anything that fits into that grid. You can depict anything. You just have to find the right keyword. And I did. So this is Pac-Man eating that formula, which is being shaped by a monster from the game. And that's the keyword. It's basically just, well, divided by 2, the original one. About the applications of that formula, there's really nothing much to say. It's just been widely used for teaching computer graphics and for decoding bitmap images. Well, that's it. And there's another keyword here I found, and so that's it. That's sources if you like. Feel free to ask me.
Excellent report, but it doesn't look like cutting-edge technologies in computing. Why have you chosen that very aspect, which seems to be a little bit outdated, in modern
Well, it
times?
might be outdated, but still it's a very interesting part, and still it's being widely used to teach computer graphics. You can, on that principle, you can build a source code, you can write a program that will depict its own source code and print it out. So it's really widely used, and today, even today, bitmap images are quite widely used. So that's, I would say it's out of date, but still, it's quite an interesting technology, and I guess that you'll find it interesting. Well, I did, because I came across it not quite long ago, just about a couple of months before this presentation, and it really got into my heart. Just because it's so unusual and so interesting and even a little bit magical.
So it is what stands behind pixel technology, yeah? What's the new trend? Have you heard of it?
Well, the new trend, just based on what you think about the new trends and what you base on that.
Yeah, like dynamic images, splitting image into layers,
well,
features.
That is actually different technology. Bitmap images are very well old, of course, but still, I mean, we speak of vector graphics, and you speak of vector graphics, I think there are different principles involved, so I guess it's not applicable to that.
Thank you. These are all good old fundamentals, yeah, so to say. Okay, thank you.
Are there some transformation of this formula that allow different colors of pixels?
Perhaps. That's really, as I've said, that you can, even based on that principle, you can just print out the source code of your program. So you may find one or two examples of such a formula, but I really haven't. So I can't answer this question with enough better ones, sorry. So,
Are you sure that the floor function of 3.999 results in 3?
Absolutely.
So,
yeah.
And what?
You just round to smallest integer.
Notice if I say that 3.999 equals to 4.
Well, it will be ceiling function. There are two functions, ceiling function and floor function. Ceiling function will round it to the biggest integer and floor function to the smallest integer, no matter how the value is.
What I mean is that the 3.999 is actually 4.
Well, some will argue, because I'm just not that good with maths to...
Maybe 3.999.
Well, yeah. Okay. So, any other questions?